So following on from our previous video, we're trying to understand why related rates work. So going back to our example, the oil tanker spilling oil, we would find something that connects everything, and it is this formula that connects everything. When it comes to related rates, we can differentiate it with respect to time, and then that will then give us this. And then for some reason, we can just plug this in, and then we can work this out. We blindly do this without really understanding why it works. What does it mean even? What does dA by dt really mean? Why is it that you can even differentiate it with respect to time? So we're going to try and understand why it is that we can jump from here to here. So let's start by drawing a graph of A versus the radius. So plotting this graph will then give us this. Will then give us this. So it's like looking at this. It's like me giving you asking you to sketch this graph. So so that will then give you this, but we don't really care about the negative side. So that will then give you this. So now let's look at a simpler version. Let's just look at y equals 2x. Now, if you differentiate this, dy by dx equals 2. So so what that means is this here is a straight line. So it's going to be y equals mx plus c. But the intercept is 0, so we can forget about the c. And the gradient here is 2. So m equals 2. So what you've got here is m equals 2. Now if you know the gradient is 2, then if you know this distance here, let's call it delta x. If you know delta x, then you can times it by, well, you can multiply it with the gradient. That will then give you dy. That will then give you delta y. So so when you have this here, if you differentiate it, dy by dx equals 2 times both sides by dx, that will then give you this dy 2, and then you've got your dx. So what that means is, if you know the small change in the x direction, you multiply with the gradient. It will then give you the change in the y-axis. And remember, the difference between delta x and dx is this. When you talk about delta x, in your mind, think of a small change in the x direction. So maybe think of something along this line, just a really small distance. But then when you're talking about dx, you're really talking about the realm of limits, and it's something heading towards 0. So really, when you think of dx, you're really thinking about 0.00000000000, a really small number. Let's say 376 or whatever. When you think of dx, you're really thinking about the realm of something heading towards 0. So it's going to be a really tiny number. Dx is a small number, but it's manageable. You can use a calculator to mess around with this number. But when it comes to dx, in your mind, you've got to think of a really small number. Your calculator cannot handle this. The point is that dx is a small number. Sorry, delta x is a small number. Dx is a really small number. But the thing is, when you have this here, you do have the right to do this. Differentiate this, dy, and then differentiate this. That would be 2, and then dx. So what that means is, if you know the change in the x direction, you multiply it with the gradient, and then that will then give you your dy. So now going back to this, differentiate this. That would give you dA by dr equals 2 pi r. You can times both sides by dr, so that will then give you dA 2 pi r dr. So what that means is, if you have the gradient, bear with me. If you know a small change in the x direction, and then you multiply it with the gradient, that will then give you the your dy. But then when you're thinking in terms of limits heading towards 0, then if you know a small change in dr, then multiply it with a gradient. So if you have dr, multiply it with a gradient, that will then give you your dA. That will then give you your dA. So the point here is that when you have this, you do have the right to do this. dA, so this will then give you this, equals, differentiate this, 2 pi r, and then dr. You do have the right to do this. This is your gradient. So a small change in the r direction, multiply with whatever this thing may be, that will then give you the change in the area. So what that means is this: a small change in the radius. So if you have a small change in the radius, and then if you multiply it with whatever this thing may be, your gradient, that will then give you, bear with me, if you start out with a small change in the radius, so if you start out with a small change in the radius, that's this thing here, and then you multiply with this thing here, that will then give you dA. That will then give you this thing here, the change in the area. If so a small change in the radius, merge it with whatever this thing is, and then that will then give you your change in the area. So if you have your change in the area, you can work backwards to find your dr by using this 2 pi r thing right here. So the relationship here is that if you have this, dA equals 2 pi r dr, you do have this kind of relationship here. A small change in the radius, merge it with this thing here, and it will then give you your dA. It will then give you your change in the area. Okay, so I hope you can accept this, and we will proceed in the next video. Okay.